get started. So, good evening. We can get started now. Other people will continue joining as we proceed. Let me present my screen. And as I present my screen, first I would like to clarify some 2 questions that were asked last time. I'm waiting for the board to open up. Someone had asked about whether the step function is vertical or horizontal. Whether the step function was vertical or horizontal. Yeah. Okay, here are the pens. So first I want to clarify why the step function is horizontal. And so I just want to consider a hypothetical case. So if this is our f-axis and this other one, the y. So on the vertical axis, f of x, which now we know represents probability, f of x, we have f of x, which represents the probability. I'm trying to write there and let me try again. So we have our vertical axis and the horizontal one. And on the vertical axis, we have f of x, which we know actually represents the probability. And then on the x-axis, on the horizontal axis, we have the x values, maybe 0, 1, 1, followed by, let's say 2. Maybe these are the only values that x takes. So if we, and then, oh yeah, we said that if we are plotting the probabilities, we can represent that by a straight line, whereby the tip of the line corresponds to the probability of the particular random variable. So the tips are corresponding to particular probabilities on the left side, so now we had said that the cumulative distribution function, capital F of x, the cumulative distribution function, capital F of x, is given by the probability that capital X is less or equal to a particular value of small x. Capital X is less or equal to a particular value of small. So if we want to plot this cumulative distribution function, one thing we know is that the maximum value of the cumulative distribution function should be 1. It goes up to a maximum value of 1. So if we have 1 over here, so when, let's say, x is 0, we have x is 1, and we have x is 2. So you see, suppose in the PMF, let's say this corresponding value here was 0.3. So it means that, and then let's say this, the second one will correspond to 0.5. 0.5. So for the cumulative distribution function, when we are starting from 0, let me use a red pen to explain better. So if this is 0 here, between 0 and the 0 for our random variable, there's a difference between 0 at the intersection of the axis and 0 for our random variable x. That 0 there is for our random variable x. So between 0 and the 0 for our random variable x, the probability, the cumulative distribution function is 0. Why? Because when we start from 0 for the small f of x, we start having probabilities when we reach the point 0, when the random variable x takes value 0. At that point, the probability is 0.3. So coming to the cumulative distribution function and remembering that it represents probability capital X is less or equal to a particular value of X. So before the point 0, there is no probability. That is why, actually, if you were to draw the line representing the probability between 0 and 0 as a random variable, then the line you'll draw will just be lying on the horizontal axis. But the minute you reach 0, which is the random variable x, the probability jumps to 0.3. So now here we have 0.3. So there will be a skip, and then now this probability will continue being 0.3 up to a point before 1. Why is it continuing to be 0.3 after 0 and just before 1? Because at the point small f of x is 0, we saw it was a probability of 0.3. And remember, it is cumulative probability that capital X takes value less or equal to X. So when we reach the point random variable 0, the probability is 0.3. And because of being cumulative, it continues. That probability now continues. It continues. And that's why we have a horizontal line. Then when we reach just before random variable 1, if we look at small f of x, at random variable 1, the probability was 0.5. So coming to capital F of x, when we reach the point 1, it will be, because it is cumulative, this our horizontal line now will go to 0.8. Why is it 0.8? Because we add the previous probability of 0.3, we add it to 0.5, we end up with 0.8. So after the point 1, and because it is cumulative, cumulative means you add all the previous and you continue with them. So adding 0.3 and 0.5, we get 0.8. And so it continues up to a point just before 2. And obviously, the last one should be 0.2 to make sense. To make sense for probability, the value here should be 0.2, though the way I've drawn it doesn't seem like that. So that when now we reach the 0.2, we add 0.8 to 0.2, and then we shall end up with 1, and 1 should continue indefinitely. So for that student who had asked whether it is vertical or horizontal, I just felt that if I share this, it will make it a little bit more clear. Then there was the other student who had taken a screenshot, and if at all I had understood what he or she was asking, let me just go back. So when that other student, I think where the other student took a screenshot, there was a circle there. But what I was saying was that it was the example that I had given, and so we're writing the form of the cumulative distribution function, and I had written 0, and that was when x is less than 1, x is less than 1, and then there was a circle here, and where that circle was, I had said that you write what we had calculated, which we found to be x over 40 into 3x, 3 plus x into 3 plus x. And I think this is the part that the student had captured on the screenshot. And the values of x were x is 1, comma, x is 1, comma, 2, comma, 3, comma, 4, comma, up to 5, comma, and below that distribution function becomes 1 when x is greater than 5. When x is greater than 5. So I think this is the part the student had captured on screenshot, and so I just wanted to clarify that. And this is the portion which I had circled in red. That is how we write our cumulative distribution function. Okay, after clarifying on that, now we can proceed with our topic for today. So last time we were considering cumulative distribution function for the discrete case, for a discrete random variable. And for the discrete random variable, we said that the cumulative distribution function, which is capital F of x, is given by summation of t less or equal to x, t less or equal to x. Sorry, how do we write that? Less or equal to x. And we were introducing t for the sake of summation, and then we said f of t, f of t. And maybe now when I write this and you relate to my first explanation of small f of x and capital F of x, maybe now it makes more sense. So this was for the discrete case. Now let us consider the continuous case. So cumulative distribution function for the continuous case. for continuous case, for continuous case, or for the continuous random variable, whichever, for the continuous random variable. Should continue to bear in mind that the cumulative distribution function, capital F of X, is given by probability, capital X is less than small value of X, is less or equal to small x. The same principle applies, only that there's a difference when we have discrete case and for continuous random variable. So we just write if capital X is a continuous random variable, if capital X is a continuous random variable with PDF. Now I am talking about PDF because we are considering the continuous case with PDF small f of X with PDF small f of X. Then capital F of X is equal to integral from minus infinity to X, integral minus infinity up to X, f of t dt. Again, we're just introducing t for the sake of integration. So for the discrete case, we sum. For the continuous case, we integrate. But remember that we are integrating up to random variable small x. Let's do an example. Let capital X be a continuous. Let capital X be a continuous random variable. Let capital X be a continuous random variable with PDF f of X, small f of X, because we are talking about a PDF with PDF f of X equal to a half X, where X takes values, X lies between 2 and 0. X lies between 2 and 0. And it is 0 otherwise. 0 otherwise. Hey. And it is 0 otherwise. So the questions are these. The first part, obtain the CDF obtain the CDF of capital X, obtain the CDF of capital X, and sketch its graph, and sketch its graph. And then part 2, part 1, obtain the CDF of capital X and sketch its graph. Part 2, compute probability, compute probability X greater than 2 over 3, X greater than 2 over 3. Then we shall, after we get the CDF, we compute this probability. Now, to get the cumulative distribution function, we have said that we just integrate from a particular value up to small x, and for this, in this example, we shall integrate from 0 up to random variable x. Oh, sorry. Now that one, it's overlapping to give the wrong impression. We will integrate from 0 up to x, a half of t dt, a half of t dt. So where is the t coming from? This t is introducing it to replace that x for the sake of integration. So if we integrate this, we will get, that is t squared over 4. T squared over 4 t squared over 4 from 0 up to x, from 0 up to x, and so capital F of x will just be equal to, capital F of x will be equal to x squared over 4 when we perform the necessary substitution. So when we substitute the limits, then we get capital F of x is x squared over 4. So how do we represent our answer? To represent our answer, then we will represent it in 3 parts. Capital F of x, first and foremost, it is always equal to 0. We will represent it in 3 parts, not 4 parts. It is always equal to 0, and then we look at the limits that were there for the values of x. What do I mean by that? We can see that x is less than 2 but greater than 0. So before 0, the cumulative distribution function should be 0. Before this 0 for the random variable, the cumulative distribution function should be 0. And how do we denote that area or that part of the straight line which is on the left of 0? We denote that by just saying that x is less than 0. So that is the region which is before 0. And then now, in the second part, now we can put x squared over 4, x squared over 4. And we have to define for what values this holds. It is just the same values as what was given in the question. X greater than 0, but less than 2. But less than 2. And then it will be equal to 1. Now you know our space is from 0 to 2. And because we're talking about probability, the probability should be 0 at the point 0, but when we reach 2, the probability should have attained a value of 1, because we know the range of probability measure is 0 up to 1. So when does it become 1? When x is greater than 2. When x is greater than 2, it will always be 1, because we have considered our space, and our space was defined between 0 and 2. Now, so what next part? Okay, we are required to plot this. Now, remember we are dealing with a continuous random variable. So in our diagram, we will have a continuous line because the random variable is continuous. Now we shall have a continuous line because the random variable is continuous. So we can consider a number of points of the random variable. We can just let 0 to be at the intersection of the axes. Then we can say we have one here, or maybe because it is just up to 2, if this one is 2, and if that one is 1, then let's say here we have a half, and here we have 1.5 is 3 over 2. 3 over 2. So when x is 0, so actually we are substituting in to draw the cumulative distribution function, which is continuous. We shall substitute in x squared over 4. So when x is 0, we will just have 0 there. When the random variable takes value a half, when x is a half, capital F of x will be 0.06. Capital F of x will be 0.06. We are substituting in x squared over 4. When x is 1, capital F of x will be a quarter. Let's say a quarter is there. Let's say a quarter is there. So capital F of x will be a quarter. When x is 3 over 2, it will be 0.56. Let me make this to be a little bit more realistic. So when it is 3 over 2, it will be 0.56. Suppose it is somewhere there. And then when it is 2, we know it will be 1. Substitute in squared over 4. So our point will be around that region. And because this is a continuous random variable, then we join the points. But remember that when we reach 1, it will always continue to be 1 horizontally. It will always continue being 1 horizontally. Now we are not yet through. we need, okay, there's a comment. Let me look at it. Yeah, someone is asking, what about the points at x is equal to 0 and x equal to? At the point x is equal to 0 and the point x is equal to, I know you will come across a number of books. In some books, you'll find that the random variable x is just denoted as less than 2 or greater than 0. In some books, you'll find that they say less or equal to 2, greater or equal to 0. Less or equal to 2. In some books, you will find that greater or equal to less, greater or equal to 0, less or equal to 2. So that would answer our friend there, because if we say x is greater or equal to 0, then this is still the point. When x is less or equal to 2, then it takes value 1. So it is just a matter of denotation. Some books will denote as x less than 2, greater than 0, and others will denote the sample space by x less or equal to 2, x greater or equal to 0. Okay, so now we go to the second part of the question, which is asking probability that x is greater than, capital X is greater than 2 over 3, 2 over 3. Now, this probability is the same as 1 minus probability, 1 minus probability that x is less or equal to, 2 over 3. And now we have captured the values. If probability that x is greater than 2 over 3, it's the same as 1 minus probability that x is less or equal to 2 over 3. And so we use our cumulative distribution function, 1 minus probability that x is less or equal to 2 over 3. So we shall just substitute. We will substitute in x squared over 4, because that gives us the cumulative distribution function at the point x is taking value 2 over 3. So it will be 1 minus 2 over 3 squared. This is our x value. And then divide by 4. And so our answer will be 8 over 9. Our answer will be 8 over 9. Okay, there is a question there. I'm looking at it. Yes. If we were to sketch the PDF f of x, will there be a yes, yeah, there will be a line at point 2. There will be a line at point 2 because x, because as I said, maybe as I said, x is less or equal to 2, greater or equal to 0. Maybe to avoid giving you room for doubt, then I will use this denotation of greater or equal to, less or equal to, so that at the point 2, we will have a small f of x. And at the point 2, what is the small f of x anyway? It will just be 1 if we substitute in the function at the point x is 2. So the probability that x is greater than 2 over 3 is equal to 8 over 9. Is equal to 8 over 9. There's another question. Okay. Now, for this example, somebody is asking where the point x is equal to 0 should be. Where the point x is equal to 0 should be. In the previous example, I put a random variable x. When it was 0, I put it there. And even this particular case, it's not a must that it starts from the origin. If we were to put it here, if we draw our line, it would still have passed through 0, and then it would continue being 1. It will be a horizontal line after the point x is equal to 2. So that's a good question, because if I put it here, it's as if we are recognizing the 0 at the point of intersection for the general graphs that we draw. But please, this 0 here is not referring to the 0 that we always have when we draw two axes. This 0 here is referring to the random variable. So if student A drew it like this, the way I drew the first time, it is okay. And if student B chooses to move the point 0 to a place a little bit further from the introduction of the axis, from the intersection of the axis, there is no problem. Both of you are answering the question correctly, as long as you know that that 0 is referring to the random variable and it is not referring to a 0 which we always have when we start drawing horizontal and vertical axis. So either case would still be is still acceptable. So that is how we would handle cumulative distribution function for a continuous case, for a continuous random variable. I don't know whether I gave you a question for practice on the discrete case. I can't remember, but after this lecture, I will give you some 2 questions for your practice. I will check whether I had given you one on the discrete case, and then also I'll give you a question on continuous case for your practice. Yeah. So let us go to the next subtopic, mathematical, to the next major topic, mathematical expectation. Mathematical expectation. mathematical expectation. Actually, mathematical expectation just refers to the average value. It is just the average value. It is just a statistical term for the average value. But we can just write this to help us understand the concept. Mathematical expectation. Introduction. A gambler may be interested. A gambler may be interested in his average winnings, in his average winnings. A gambler may be interested in his average winnings, and a businessman may be interested in his average profits. A gambler may be interested in his average winnings, and a businessman may be interested in his average profits. A gambler may be in his average winnings, and a businessman in his average profits. Mathematical expectation. Mathematical expectation or expected value is the average value of a random phenomenon. Definition: expected value of a discrete random variable. Definition: expected value of a discrete random variable. Now you see, we want to consider mathematical expectation for a discrete random variable, and then later on we shall also consider mathematical expectation for a continuous random variable. So first of all, expected value of a discrete random variable. Let capital X, so we are defining now, let capital X be a discrete random variable. Let capital X be a discrete random variable which takes values x1, comma, x2, comma, followed by 3 dots. It takes values x1, x2, x3, and so on with PMF. Now you know what PMF is: probability mass function. With PMF f of xi, with PMF f of xi equal to probability that capital Xi, it is the probability that capital X, that random variable X takes value Xi, small xi. We have said that f of xi is actually probability where I is 1, 2, 3, and so on. 1, 2, 3, and so on, 3 dots. So we are saying that, if I can repeat, let capital X be a discrete random variable which takes values x1, x2, x3 with PMF f of xi, which is equal to the probability that random variable capital X is equal to small xi. Then expectation of random variable X. And now we know that expectation is none other than the average value. Expectation of random variable X, we call this expectation of X, is given by the summation over X, the summation over X, Xi, f of Xi, f of Xi. When we are dealing with discrete random variables, we perform summation. When it is continuous, we integrate. Now, what does this mean? We are saying that the expectation of X is summation over all the X values, X subscript I, f of X subscript I. What does this xi, f of xi mean? The one that I've underlined in red. Xi is the random variable, maybe it is 0, 1, 2, 3, and f of xi is the probability of capital X taking that random variable. For example, if f of xi is 0, we multiply it by the probability of the random variable being 0, and we sum. We will sum over I, where I is 1, 2, and so on. Why don't we look at an example? Example, a gambler is paid a number of shillings. A gambler is paid a number of shillings equal to the number of points. A gambler is paid a number of shillings equal to the number of points showing, equal to the number of points showing when a fair die is tossed. The number of points showing when a fair die is tossed. What is the expected gain? What is the expected gain of a player? What is the expected gain of a player in a single game? What is the expected gain of a player in a single game? So to get the expected gain, which is the average value, we will just sum over x, xi, f of xi. But first of all, we need to get the probability mass function. We need to get the probability mass function. When we do what are we tossing here? It's a die. It's a die. And we know that for a die, the faces of the die are numbered. The faces of the die are numbered 1, 2, 3, 4, 5, and 6. So these are the xi's. These are the possible outcomes. When we toss the die, we can get a face which is numbered 1, another one is numbered 2, another one is numbered 3, another one is numbered 4, and so on. So the gambler is paid a number of shillings equal to the number of points showing when a fair die is tossed. The number of points showing can either be 1, 2, 3, 4, 5, 6. But what is the probability of getting any of those numbers showing? The numbers are 6. When you toss, the probability of getting any of those outcomes is 1/6. And it is 0 elsewhere. So the probability is only 1/6 if x is 1 or 2 or 3 or 4 or 5 or 6. Otherwise, it is 0 elsewhere. So to get the expected gain, we shall sum over, now I can write that x is full. You know, x will start from 1 and it will go all the way up to 6 xi. The xi value keeps on changing, but f of xi is a constant. F of xi is a constant. It is a constant 1/6. So because it is a constant, we can write it here. It is a constant 1/6. But if it was also changing, then we cannot write 1/6. So this is equal to, we can factor out 1/6. And what is summation xi for x is 1 up to 6? It just means 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if we perform this addition, we get 3.5. So the gambler expects on average to get 3 shillings and 50 cents. That is on average. The gambler can get, suppose he tosses and we see a 6. So he will get, if he tosses and the reading on the die is 6, he will get 1 shilling. If the reading on the die is 1, he will get 1/6 shillings. That is some cents. But on average, the gambler expects 3 shillings 50 cents. Let us look at another example. If there is no query, another example. And now we want to look at an example which involves a probability distribution, Okay, so example, let capital X be a random variable. Let capital X be a random variable with probability distribution. With probability distribution. Now we have it in tabular form. With probability distribution. We have X at the top, f of X below. X is what? Minus 3, 6, minus 6, 9, and with probabilities 1/6, 1/2, and 1/3. So that is the probability distribution. And we know that 1/6 plus 1/2 plus 1/3 should be equal to 1. The questions are: find expectation of X, which is just the average value. And then the question goes further to ask us also to get expectation of X squared. After a few, we will see where expectation of X squared is applied. But for now, let us just get the average value, expectation of X, and then we shall also get expectation of X squared. So to get expectation of X, of course, the random variable we are considering is discrete, and we know it is given by summation of xi, f of xi, the one which is called in red, summation of xi, f of xi. So that just means that we take the X value multiplied by the probability. So like now, minus 3 is the random variable. What is the probability of observing random variable? It is 1/6 plus 6 multiplied by a half x multiplied by its f of x plus 9 multiplied by a third. 9 multiplied by a third. And this will give us 11/2. Okay, oh dear, what did I get there? Is this expectation of X squared Or is it expectation of x? This is expectation of x. Summation of x f of x. X f of x. X f of x. So now we can look at expectation of x squared. Sorry for that. Expectation of x squared. Now it just means that the random variable, like -3, we square it. That will give us 9 multiplied by 1/6. 1/6. 9 multiplied by 1/6 plus x squared. What is that? 6. 6 squared is 36 multiplied by 1/2. And then 9 squared is 81 multiplied by 1/3. 1/3. So the expectation of x squared, this one will be 93/2. 93/2. So that is how we get expected values. And you know, we can take this concept further. We can still take, and we look at an example where we do not necessarily have numerical values. We can look at a case where we are looking for expectation, but not necessarily dealing with numerical values. Suppose we look for expectation with symbolic, with some symbolic representations, like in the example that we are looking at now. The next example, a discrete random variable. Example, a discrete random variable has PMF, f of x equal to 2x over n into n plus 1 for what values of x? When x is 1, 2, 3, 1, 2, 3, 4, 5, 6, up to 'n'. So x takes those values and it's 0 elsewhere. 0 elsewhere or otherwise. 0 elsewhere or otherwise. What are the questions? The first one, show that f of x, small f of x, show that f of x is a PMF. Show that f of x is a PMF. Secondly, we are expected to find expectation of X. Secondly, we find the expectation of X. Okay, so the first part show that f of X is a PMF. And there are some properties we looked at when we were describing what a PMF is and what a PDF is. And we said that for a PMF, if we sum over the whole sample space, then we should get 1. We should get 1. So to show that f of X is a PMF, then let us try summing over the X values. You know, what are the X values? X is from 1 up to N. X takes values 1 up to N. We sum f of X over the X values. We are summing f of Xi over the X values, because we know that f of Xi actually represents probability. So if we add all the probabilities, and if it is, now put the bracket at the wrong place. The bracket should be there. So if we sum all the probabilities and we get 1, then f of X is actually a PMF. So how are we going to do that? It means we sum over X is 1 up to, we sum over X is 1 up to N f of Xi. And what is f of Xi? It is 2xi over N into N plus 1, N into N plus 1, into N plus 1. So what is that? It is 2 over N into N plus 1 summation of Xi. What is remaining? Okay, let me just write that for clarity purposes. Summation X is 1 up to N Xi. So what do we have there? So this will be equal to 2 over N plus 1 into N plus 1 and then, so what is summation Xi? We are summing the Xi values. So it means we will have 1 plus 2 plus 3 plus 3 dots plus 3 dots plus the last value of x is n. So this is equal to 2 over n into n plus 1. And you know, this 1 plus 2 plus 3 plus 4 up to plus n, it is represented in general form as the summation of I in general form. And maybe you guys have come across that summation of I in general form. What do I mean by that? I am saying that if you have used some logbooks before, then if you've used the SMP tables, summation from I is 1 to n of I is given by a half n into n plus 1. So really it's an arithmetic progression, and maybe some of you realized that it is an arithmetic progression. So summation of I up to n, that is 1 plus 2 plus 3 up to n, it simplifies to 2 into n plus 1, n over 2 into n plus 1, n over 2 into n plus 1, so we can cancel like terms. We cancel like terms, and actually, so this is just equal to 1. And because we have found that the summation of the f of xi's is equal to 1, then it shows that f of x is actually a probability mass function. Now we want to find expectation of x, and we know that expectation of x is summation summation over x f of xi, x multiplied by f of x. So we can perform that. So this will just be equal to, what is our first x value? It is 1 multiplied by f of 1, so we want f of 1, which means that where there is x, we put 1. Where there is x, we put 1. So that will be 2 times 1 over n into n plus 1 n plus 1. Okay, that is when x is 1. What happens when x is 2? So where we have x, we put 2. Then we need to multiply 2 by f of 2. F of 2, it will be 2 times 2. 2x is 2 times 2. Over what? N into n plus 1. N into n plus 1. And if it is plus 3 dots, and the last term, 3 dots, and then plus the last one will be, our last value of x is n into 2 times n, 2 times n over what? N into n plus 1. Close the bracket, close the bracket. So that is equal to what? What is common? 2 over n plus 1 is common to all the terms. 2 over n into n plus 1 is common to all the terms. Then we can open a bracket and we see what is remaining. We have there 1 squared plus 2 squared plus 1 plus 3 dots. The last one is n squared. Close the bracket. So this is the same as 2 over n into n plus 1 and then this 1 squared, 2 squared, up to n squared, actually, they are of the form of summation of I squared. They are of the form of summation of I squared. And if we go back to our tables, summation from I is 1. I'm looking at the second row now. Summation from I is 1 up to n of I squared simplifies to n over 6 into n plus 1 into 2n plus 1. It simplifies to that. So the quantity in bracket, we can write it as n over 6, n over 6 into brackets n plus 1 plus 1 into brackets 2n plus 1 and then like terms, we cancel like terms like n and n plus 1, n and n plus 1, and then 2 goes into 2 ones, 2 goes into 6 3 times. Our expected value is 2n plus 1 over 3. 2n plus 1 over 3, like that. So it is possible to get expected value even when we are dealing with random variables which are not necessarily numerical in nature. And so I will also send a question for your practice to the class rep, and they will forward to you. If there is no query, I will continue to the next expectation. Now we want to consider a continuous random variable. So definition, expected value of a continuous random variable. Expected value of a continuous random variable. So we just write the definition. How would we get that? The definition: let capital X be a continuous. Let capital X be a continuous random variable. Be a continuous random variable with PDF f of x. Now we are talking about PDF because it is a continuous random variable with PDF f of x, then expectation of capital X, expectation of x is given by integral from minus infinity to infinity of x f of x dx. X f of x dx. X f of x dx. Oops. That is x f of x, then dx. We will just integrate. Let's look at an example. Let capital X be a continuous random variable. Be a continuous random variable with PDF f of x equal to 1/18 x plus 3 x plus 3 x plus 3 and 0. Of course, 0 elsewhere. And for what values are f of x equal to 1 over 18 into x plus 3. This is the continuous case. So we are saying it is for x less or equal to 3 greater or equal to minus 3. Greater or equal to minus 3. Okay, and then we are required to calculate expectation of x and expectation of x squared. Expectation of x and expectation of x squared. So let us calculate expectation of x. Expectation of x is integral over the sample space. For this example, our sample space is from minus 3 up to 3x. And what is f of x? F of x is 1 over 18 into x plus 3. So we're just multiplying x by 1 over 18 by x plus 3 dx. And so if we perform, after performing the necessary integration, we find that this value is equal to 1. It is equal to 1 if we perform the necessary integration. And then to get expectation of x squared, of course, I expect you to perform the integrations. Expectation of x squared is equal to integral. So I'll just do this to make it easy for me, so I don't have to write all that afresh. So using the first example, I want to use it for expectation of x squared. So in the bracket now we have x squared, and so it will be equal to integral minus 3 up to 3 x squared now, f of x remains the same, 1 over 18 into x plus 3 dx. And if we, after performing the integration, this will be equal to 3. So expectation of x is 1. Expectation of x squared is 3. Expectation of x squared is 3. Maybe, okay, we continue to the next example. We continue to the next example. A continuous random variable. A continuous random variable has PDF. A continuous random variable has PDF. F of x is equal to f of x is equal to 1 over b minus a where x is less than b and greater than A, and 0 elsewhere. So what is the question? The question is, show that expectation of X is equal to, show that expectation of X is equal to A plus B over 2, A plus B over 2. And also, we want to show that, expectation of X squared or let me write this like this: X greater or equal to X less or equal to B. So we also want to show that expectation of X squared is equal to a third into B squared plus AB plus AB plus what? A squared. So let's start with expectation of X. So we are dealing with a continuous random variable. So we know we shall just integrate from A to B X f of X. F of X is 1 over B minus A. So I can just write it like that. Of course, dx. So what is that equal to? Of course, if we integrate, we know that this will just be X squared over X squared over 2 into B minus A from A up to B, from A up to B. So let us substitute for X squared. So it will be B squared minus A squared over 2 into B minus A, and what is this equal to? You know, B squared minus A squared is a difference of 2 squared. So it is B plus A into B minus A divided by 2 over B minus A so what is that? B minus A cancels with B minus A, and then our answer is B plus A over 2. And so we have shown the expectation is A plus B over 2. Oh, sorry for that. My electricity just disappeared. It just went off, and it looks like it is unstable right now. Let me look at the chart first. I had called one of the class reps, and I told the class rep what was happening. So I can just see, no. Is that, I don't know, my electricity just disappeared. So let me look at the chart first. I'm looking at the chart. So let us continue, hoping that my electricity will not just throw me out again. Oh, I can see the recording is still going on. So let me present my screen. And I hope it will take me to where I was cut off. Yeah. And it's like there's a comment on the chat. Let me look at that first. Okay, somebody with a broad smile is asking something about network breaks, leaving some huge gaps in the nodes. Surely it is I know we have network issues, so that's why I'm recording, and then I will make the recording available. I will make the recording available. If some of us can have challenges, I know you have more challenges than us, so I will make the recording available. Okay, so before I was rudely thrown out by lack of electricity, because I'm using Wi-Fi, then we had shown that expectation of X was equal to A plus B over 2. So I'm remembering that smile from that student, and it's making me very happy. Otherwise, let us try to show that expectation of X squared is equal to 1 over 3. So we just go through the same steps. So why can't I just make this one very easy before the electricity chucks me out? So expectation of X squared, now I can rub from, let me rub this. And then now we make this one, okay, let me use a red pen so that everybody can see. So now we make this one expectation of X squared is equal to integral from A to B of X squared now. X squared f of X. X squared f of X, which is X squared over B minus A dx. Oops, sorry for that. So this will be equal to, if we integrate, it will be X cubed over 3 into B minus A. X cubed over 3 into B minus A. So we substitute for X cubed by B and A. So we have B cubed minus A cubed over 3 into B minus A into B minus A. But we have still not shown what is required. So what do? We perform long division. So now I'm writing at the top on the right side, that is B cubed minus A cubed. We're just using all the type of maths that we know to show what is expected of us. We are dividing that by, let me remove this because we are used to square root sign so much. So we are dividing B cubed minus A cubed We are dividing by b minus a, b minus a. So the first factor, we can make it b. So b multiply, no, not b. It will be b squared. B squared multiplied by b, that one will give us b cubed minus a b squared, b squared. Okay, so let us perform the subtraction. B cubed minus b cubed is 0. 0 minus ab squared, that will be a b. We are subtracting like terms, that is ab squared minus a cubed. Subtracting like terms, b cubed minus b cubed is 0. 0 ab squared minus ab squared is ab squared minus a cubed minus 0 a cubed is that. The next, so the next factor will be ab. So what is a? Actually, it is it positive or negative? It has to be positive, so that if I multiply ab by b, I get ab squared. So ab times b is ab squared, and then ab times minus a is minus a squared b minus a squared b. So ab squared minus ab squared, that is 0, and then 0 a squared b minus a squared b, that is a squared b, and then minus a cubed minus 0 a cubed, that is just minus a cubed. So then the next factor will be a squared plus a squared. So a squared times b, that is a squared b minus the next term will be a squared times minus a, that is minus a cubed, and of course we are done. So going back to the left at the bottom, then this is equal to what? So actually b cubed minus a cubed over that. So it is just 1 over 3 into those factors that we got there, b squared plus ab plus a squared. I can see there is a question on the chat. I'm going to address that very soon. So we have shown that expectation of x cubed is equal to a third into b squared plus ab plus a squared. Let me take the question on the chat, and before that I want to find out the people who have not left because of network. So now let me look at the chat. So what is the chat saying? A question, somebody is asking whether there should be a 6. I don't think so. This is Brother Mutisia. There should not be a 6. No. There should not be a 6. It's just okay the way I have done it. There should not be a 6. We don't have 6 there. We have letters A and B. Any other query? So there being no other query, And one of you having been very happy that I was thrown out because of lack of electricity. Why don't we call it a day? We can call it a day, and you can have a good evening. Have a good evening. Bye. Have a good evening.